So welcome to this class on software-defined networking. And so we will talk about what is SDN, what are the different SDN controllers, what are the different protocols that are used with SDN, and then a brief introduction to RESTful APIs and OSGI framework. So origins of SDN. SDN originated with OpenFlow. And basically, we already had a class on OpenFlow, and you know that OpenFlow means centralized controller. And as soon as the centralized controller came in, people said, wow, we can control the whole network from one single place, and therefore we can choose. So initially, SDN was defined as just similar to the OpenFlow, which means you separate the control and the data plane, centralize the control plane, and you use OpenFlow to talk to the data plane. Okay. Now, over the years, the definition has changed significantly. I think that definition was in 2010. Okay. So now, 7 years later, the definition has changed. Now, there are now what SDN is defined as is first the abstraction of the hardware. So basically, one thing with SDN now, if you say SDN, what it means is they call it disaggregation as well, is that it doesn't matter what hardware you're using, whether you're using a router from company X or a router from company Y or your own router, it should not depend upon that physical infrastructure. Second thing, programmability. You should be able to change anything sitting at one place. And third is the centralization of policies. And this is different from control. Policy, delegation, and management. So you can say, well, I want this policy. This is my policy, and I will give you some examples of policies in a minute. But basically, policies are different from control, as shown in the next slide. And you set your policies that these people, for example, Department of Computer Science is not allowed to access computers in Department of Electrical Engineering. And that is your policy, right? So you can put the rules as to what you want, and that is what SDN is defined as. So why do we need SDN? Well, SDN provides a lot of stuff, and that's why it has been so successful. First is virtualization. Since the physical infrastructure does not matter, it could be a virtual infrastructure, and therefore it doesn't matter where the resource is located. It could be in the cloud, it could be right there, it could be anywhere. Orchestration. Orchestration means, just like in an orchestra, a single person, the director, plays his stick, and then suddenly the whole tune changes. So that is what is called orchestration. You can, sitting at one place, you can change a lot of devices. Programmability, obviously we talked about that. Dynamic scaling. You can change your network size from 10 routers to 100 routers back to 10 routers. Just like we do in cloud computing, for example. Automation, and then basically everything can be automated from troubleshooting to downtime, and policy enforcement to provisioning. Provisioning means bringing new devices in, re-provisioning, or segmentation of resources, or you want to segment from department by department. You can add new workloads, size devices, so everything can be automated. Visibility. You can monitor the resources from one place. And then performance, of course, because now you can optimize the network device utilization. And multi-tenancy, a lot of people can share the network. And service integration. And you can put everything like not just routing, but also load balancers, firewalls, intrusion detection systems, etc. can be provisioned. And finally, the openness. Basically, full choice of all mechanisms you have. You can change any layer of the API, as you will see in a minute. And so you can, your software is not reliant upon a particular hardware, and the hardware is not reliant on particular software. So you can change either one at any time. That is what defines SDN now. And SDN has been so successful that it is not just SDN, it is SDX. So now we have software-defined data center, software-defined storage, software-defined compute, software-defined infrastructure. And as this cartoon says, everything but the kitchen sink is software-defined these days. Okay? And you can have anything you're talking about, and you can say, let's make it software-defined, and people will say, yeah, that's a good idea, a new idea. And so everything is software-defined. Basically means that everything can be programmed. And so this is like a tsunami, as shown in the other cartoon, which has really taken over computing. So first of all, why centralized? 60 years ago, or actually not 60 years ago, yeah, almost 57, 60 years ago, in 1960s, 68, 50 years ago, the United States government said that we don't want a centralized network, and therefore, which was a telephone company at that time, we want a distributed network. So we invented internet, and internet, everything is distributed. And so far, we have been preaching to all the networking students that distributed is good. And now suddenly they are saying centralized is good. So what is good about centralized? This debate about centralized versus distributed has gone on forever. So basically, the advantage of centralized is fast response to changes. In the distributed manner, like in OSPF, if the link goes down, you tell your neighbor, the neighbor tells their neighbor tells their neighbor, and so on and so forth. And it goes on for a long time before everybody knows that one link has gone down. With the centralized manner, you just call your boss and say, well, I'm sick today, and then everybody in the company knows that you're sick today. So centralized is very fast. Fast consistency, and therefore everybody knows the exact information in the centralized stuff, whereas in distributed manner, everybody has a different piece of information, and that may not be consistent. It is less overload because you don't have to send any square messages, wherever in the distributed, you send any square message, everybody has to tell everybody else. There are lots of messages. And the one negative point about centralized is single point of failure. If the boss, something happens to the boss, then what do you do? And in the case of distributed, there is no boss, and therefore it is fault tolerant. And that was the main reason why internet was invented, because they thought that if Russia were to bomb the headquarters of AT&T, then you won't be able to talk to anybody in the United States. Nobody will be able to talk to anybody, and then that is a single point of failure. So anyway, given that actually, and now we are 50 years later, 2 generations later, we are thinking differently. And basically, centralized is good because that is how all the organizations run. Our company, our university, our school, our department, everything runs in a centralized manner. We all have a boss, and the boss has a boss. So why not? So basically, that is why now the centralized is back. Any question about this? No question, then I will move forward. So basically what SDN is not. A lot of people will, the SDN still is not very clear to many people. And some people will define SDN as open flow. Some will say that SDN is a standard southbound protocol. And southbound means control is on the top, and in the data plane is on the bottom, generally in the picture. And therefore, southbound means control to data plane standard API. Some people think that the centralized control plane is SDN. Others think that the separation of controlling the data plane is SDN. Now, these are not SDN because these are mechanisms. This is how you get there, not there. Sitting, if you want to go to the top of the mountain, there are many ways to get there, and so these are the ways to get there. And these are not the only ways to get there. And therefore, to define SDN, you really have to understand what it is, right? So this is not the mechanisms, it's a framework. And there are many solutions for that framework to get there. Okay? So that is what we are going to talk about. So there are 4 key confusions about SDN. First is people cannot distinguish between policies and control. Control is all the bits that are not sent by the user, but they are required for getting the message from here to there, those are control bits. You know, I mean, basically the user sent the payload and then we added the header to it. Those header bits are control bits. Okay, we added a routing table, that is a control bit, and so on and so forth, right? So basically that is not policy. As you know, I mean, policies are very different. Policies are written in English and not in bits. So policy versus control. Second confusion is separation of control plane. And separation of control plane, many people think that means that the forwarding, the data plane will have no brain, will have no control. They cannot decide what to do, and then the controller decides everything. So that is a separation. SDN versus OpenFlow. OpenFlow is the father of SDN, but not SDN. As I said, OpenFlow is just one of the protocols in the SDN, and there are many others. So need OpenFlow. And the question is, does we really need OpenFlow? And the answer is yes and no. OpenFlow is micromanagement. It is not scalable for large infrastructure, for scalable solutions. So we need some automation, some other ways to do the productivity. Now, this cartoon clearly explains the difference between control plane and policies. On the left, all the control planes from the data plane has been removed, and they cannot think. There is only one brain which is controlling the whole plane, right? On the right, you see the policy. One person on the right decides the policy, tells to his five subordinates. Those five subordinates tell to the other five subordinates and first subordinates, and in a minute, the whole country is going in one direction. Okay? But everybody has a full brain. Everybody can make decisions independently, but the policies are enforced. That is the difference between control and policies. You cannot just hope that things will be done in a very large organization where one controller decides the whole thing. So that is the difference between control and policy. Any question about control and policies? All right. So current SDN debate, what versus how. So basically, some people think how you do it is SDN, and some people think what is SDN, right? So that is the thing. You have to understand what is SDN, not how it is done. Because how is many different ways. Okay, we already saw 4 or 5 different ways of getting there, but we will talk more. And complete removal of control plane may be harmful. If you just remove the whole control plane from every device, then the device may become dumb, and it may be a problem. So really, at this conference today, 7 years later, I mean, the SDN has been around for now. I think it was started in 2012 or something in that time frame. And now, 5 years later, we call it disaggregation. Disaggregation simply means that the hardware and the software are not aggregated. Previously, when you bought a router from, let's say, Cisco, you got the hardware from Cisco and you got the software from Cisco. If you bought the router from some other company, the same thing applied. Today, you can buy the hardware from one company and get the software from another company. And that is what is happening. That is what SDN is all about, is disaggregation. So, complete remote control plane hardware. And the SDN is easy with the standard southbound. About the southbound protocol, yeah, it's easy if everybody spoke the same southbound, but we all don't speak the same language. We don't use the same operating systems. We don't use the same processor. But still, we can do the same things, right? So that's the thing is that, standardization is good, but it is not required. Industry finds an easier way to solve the same problem by another method, they will win. So the mechanisms are not important. What is important is the goal. So there are 4 flavors of SDN. One is Open Daylight, which I will explain in the next few slides. Multi-protocol southbound. Second is bare metal switches and the network operating systems. And actually that is I just say is called disaggregation. Basically, now you can buy what they call bare metal switches. Basically, the hardware you can buy, Dell sells it and many other companies sell it. You buy the hardware from them and you can install your own software on it. And one of the software pieces that is used, just an example and not required, is ONI. ONI is Open Network Install Environment. So you can run ONI, and then you have, and then on the top of ONI is just the operating system. And then on the top of that, you can run your own software, which could be a routing software, switching software, BGP, OSPF, or whatever you want to run. You run on the top of that ONI. And so that is another way of SDN. Third is VMware NSX. And so VMware is in the virtualization business, and they have their own way of virtualizing, and they call it SDN. And ONF SDN, and then ONF is Open Networking Foundation, for which the SDN simply means open flow. If you use anything other than open flow, then they call it impure SDN. That is not pure SDN. Pure SDN for them is open flow, and I think that definition has been largely ignored. So now southbound is basically not standard and not required to be standard. Anyway, all of these flavors of SDN provide the three things that we talked about. They all provide abstraction. They all provide the hardware and the software. They all provide programmability, and they all provide centralization. So at one place, sitting at one place, you can program the whole network. So one of the SDN controllers which originally came in was the Floodlight, and it was developed by a company called Big Switch Network. It was written in Java, and they had basically a software called Indigo, which will make any switch hardware open flow compatible. And so this controller can be used basically, as you can see the picture. In the picture, they are showing some open flow hypervisor switches in the bottom, and then Indigo data plane interface in those switches, and then the Floodlight controller can talk to them. And on the top of Floodlight, you can put your apps. They call it apps, where apps could be routing, OSPF, BGP, whatnot, anything, circuit, so on and so forth. Now you can see clearly the north and the south. The top is north, the bottom is south. So between the controller and the apps is the northbound API, and between the controller and the bottom is the southbound API. Okay, and I have written here REST API. I will explain REST in a minute, but basically, so now you can see at least that there is a controller and there is a northbound and a southbound. Okay. Now they had a number of real-world networking applications. They had a Neutron plugin. Now, Neutron is not part of Floodlight. Neutron is part of something called OpenStack. OpenStack is the software that is used for the cloud management, and we will talk about that when we talk about the clouds. And so Neutron is the OpenStack cloud management system, and so with this, you could then control the cloud and say, well, give us the 2 routers, or give us the 2 VMs, or give us whatever. A static flow pusher, and that allows you to put not only compute the path, but you can just say, okay, no, I want everything going from A to B by this path. Circuit pusher, again, same thing, permanent entries and all the switches, firewalls, and big virtual switch. And you can create a big switch out of many small switches. Okay. So all of these features are of Floodlight. Now it is really not important to know much about Floodlight because you will not use today Floodlight. Floodlight has come and gone. Floodlight actually has become Open Daylight, and which is what we use today, and I will talk about that in the next slide. So not the immediate next, but after that. So ONOS is the Open Network Operating System. And so this was the controller that came from Stanford, from the people who designed OpenFlow. And one of the problems was that everybody else's controller, basically, they are doing different things, and so they wanted to have a controller which actually did OpenFlow on the southbound. And so the picture that you have is actually now 2 years old. That's an actual picture from some ONOS documentation. However, today the picture looks much more complicated. And the purpose of this picture on my screen is basically to show you that the controllers require a lot of different pieces. And I'm not going to go through these pieces, just want to show you the variety because the next slide, Open Daylight, we will discuss these, some of these pieces anyway. So initially it was OpenFlow only. Now you can see at least it says multi-protocol southbound, although I don't see many southbound protocols. The still picture shows OpenFlow only, and that comes and was OVS-DB. OVS-DB we have talked about as to how to manage a vSwitch database. NetConf is net configuration, which is like SNMP, and then OpenFlow is OpenFlow, And then on the left it says OSGI, and which is actually we'll talk about at the end of this module. Towards the end of the module, we'll talk about OSGI. On the northbound, now it talks about REST API, and again the REST has to be defined. GUI is the graphical interface, and CLI is the command line interface. So this is common among all these systems that we will see. All the systems that we will see anywhere now, they will have three APIs: CLI, GUI, and REST API. And then on the top of that, you can have your applications. So the next operating system is Open Daylight. Our next controller is Open Daylight. And so when Open Daylight started, this was a step away from Open Networking Forum because people wanted more freedom than what Open Networking Forum would allow. And so they branched away and went to something called Linux Foundation. Linux Foundation is the one that manages the Linux operating system code. And the Linux operating system is open software. Anybody can write the software, anybody can use the software, and so on and so forth. And that is the kind of freedom that the industry wanted. So they started Open Daylight under Linux Foundation. And so this one, when it came right up front, this one actually came with a lot of protocols on the southbound. As you can see, there is something labeled southbound protocol. And you can see there is OpenFlow, there is OVS-DB, there is PCE, and I will talk about that in a minute. There is SNMP, SXP, BGP, you name it, every protocol is there. And then there are network elements. And below the network elements, we have these tunnels that we have already talked about, like VXLAN and VGRE and so on. The magic in this, in OpenFlow, Open Daylight, was the service abstraction layer, SAL. So before service abstraction layer, basically on the top of that, you have lots of applications or lots of modules, and they will decide to do something, and they will give it to SAL, and the SAL will translate into whatever is southbound. If somebody speaks OpenFlow, SAL will give it to OpenFlow driver, and the OpenFlow driver will then give the OpenFlow commands to the OpenFlow device. If it is, let's say, just for a second, it is a PCE device that uses PCE, and I haven't defined PCE, but it is coming up in the next slide. Then the SAL will give PCE commands, PCE to talk to the PCE driver. These are all drivers, PCE driver, and PCE driver will speak PCE to the PCE device, and so on and so forth. So this was one thing, is multi-protocol southbound. There are many protocols that can use southbound now. And then you can see there are a lot of things which are required, and they are basically categorized into three categories. Basic network functions such as switching, hosting, and tracking where the hosts are, forwarding rules, etc., etc. Then there are enhanced network services to make them better, such as AAA, which is authorization and control, and NetIDE, Internet Development Environment, and so on in the middle. And then network abstractions is basically something that can somehow, abstract the hardware and tell me what hardware interface I have. Right? On the top of that, we have AAA authentication filter. So security is on the top. So before anybody can do anything, they have to be authorized. So AAA is authorization, accounting, and authentication. Something like that. And then on the top of that, we have APIs, and then you have a GUI, like we said before. GUI is the graphical user interface, and in this case, we use Glux which is a particular graphical user interface, Deluxe. And just like, when you use HTTP, you can use Firefox or you can use, Internet Explorer. Here they are using Deluxe. And then they have APIs which are REST or RESTConf or NetConf or AMQP. And then they have OSGI framework. So I have to explain to you later on what is REST and what is OSGI. But this picture basically tells you the intent of the industry, that they really wanted a freedom in defining southbound, northbound, and to be able to plug in the modules. So each of these words that are there, and there are many of them, these are modules that people wrote from different places, or in fact, collaborated in writing in from different companies, and now they can be part of Open Daylight. Okay? So the Open Daylight is the most commonly used SDN controller. And so this is also called OSCP, Open Daylight SDN Controller Platform, OSCP. And there are hundreds of companies involved under Linux Foundation. The conference that I'm in is actually Linux Foundation conference. And there are many projects here now, just not Open Daylight. Now there are hundreds of projects, and we can talk about those too. But Open Daylight was the first one. And Open Daylight first networking project, let me put it this way. Because after Open Daylight came in, lots of other things came in. And now there are hundreds of projects. To support multiple southbound protocols web plugins, and so you can have not only OpenFlow, but you can have many. And the magic is in this abstraction layer, SAL, and modular design using OSGI framework. So OSGI is a framework that has been developed by the industry, and I have to explain to you later, that allows you to make modules from different places and then combine them. And it has a rich set of northbound APIs by RESTful services and loosely coupled applications. Okay. Any questions about Daylight, Open Daylight? Okay. Then the examples of the alternative APIs. So southbound APIs we saw like TCP, BGP, northbound API we saw Alto, and the overlay we saw VXLAN, Trill, and Lisp. And the configuration APIs are NetConf, RESTConf, controller is PCE. So we will explain some of these things that we have not explained. We have already talked about VXLAN and Trill, so I'm not going to talk about the overlay layer. NetConf is actually will be discussed at the end of this class. This is the last lecture in this class, in this course, is on NetConf. It needs more than a few slides. And I might add RESTConf also there. But so basically, let's see some of these things that are APIs that we have done. So one of the first things is Path Computation Element, PCE. So what happened was that this is a long time before software-defined networking. When MPLS came in and the GMPLS, generic or generalized MPLS came in, then they required the routers to know the path that satisfies some constraints. So if a carrier wanted to set up a path from Boston to San Francisco, they would say that I need a path which is 100 gigabit and which has so much delay and so on and so forth and so much minimum bandwidth. And so there are multiple constraints. And then they would also need to have a path which does not use any of the routers that are used in the backup path, or they want to set up a backup path which does not use any of the routers in the forward path. So all these constraints are difficult to do distributed manner. So what they needed was that they said, okay, so they found a group called Path Computation Element, PCE. And PCE element actually is more like a centralized controller which has a complete view of the whole network and can compute the path with all the constraints. And then when somebody asks them, is there a path from Boston to San Francisco, it can give it to them. Right? So as shown in the picture in the bottom, there is a path computation client, which is the router which wants to start setting up an MPLS path but has no idea of the network. So it will ask the thing on the right, which is called path computation element, which is actually the controller, which actually knows the whole picture. So it will ask them, then it shows that, and it will ask the left, will ask the right, what is the 1 gigabit per second route to New York not going through Boston. And so there is a whole database here in the PCE, and it will give the answer back. So this protocol was already designed long time ago. So people said we already have software-defined networking using this. So and so on and so forth. A lot of people pushed for this, and so it still exists. There were already some modules. So PCE is one possible southbound interface. Now notice that there is no separation of control here. It is separation of policies. So the policy is designed by the PCE. If somebody says that nobody should ever go through, Toronto, then nobody will go through Toronto, period. And so the policies are different than control. Control is, that deciding, the details, where the policy is this, overall goals. So the PCE can be centralized or may be distributed in one or many routers. You don't have to have one PCE controller. You can have many PCE controllers. All of them can have the same information or may have even slightly different information. But basically, you go to your nearest PCE and ask them. So PCE separates the route computation function from the forwarding function. Both functions can be resident in the same box or different boxes. There are 25 plus RFCs that have been written on PCE to PCC communication. PCC is the client. And PCE to PCE communication when there are multiple PCEs. And PCE discovery, how do you find the PCE? So all of this is already done a long time ago. So that is one possible southbound. Okay? Any question about PCE? Okay, if you say no, then at least I know that you're hearing me. Okay, good. So the next protocol is ALTO, Application Layer Traffic Optimization. And so there is an IETF working group that was done. Again, this is much before software-defined networking. It was done to optimize P2P traffic. P2P traffic is when you download a file from the internet using, one of these P2P protocols or programs. Then you ask where the file is and who are the seeds, and you might get the seeds in Germany while you are in New York. So they said, why don't we have some optimization of this so that everybody who is in New York can get the file from New York and doesn't have to go to Germany. And so better to get files from nearby peers. And so to provide this kind of guidance, they developed a protocol called ALTO, Application Layer Traffic Optimization. So the ALTO server has the knowledge of the distributed resources. It knows where the files reside. And ALTO client go to the server and say, please tell me where the files are. And then depending upon your distance, depending upon how much you're paying, it will tell you where the files are. And they could get the information from the providers or from the nodes or things like that. Right now, actually, we have something similar in P2P, where you go to a place where you can find out who has the file. But those people, they don't tell you and that the file and this guy is in Germany or something. All they have is a list of IP addresses. So you get a list of IP addresses, and then you have to measure the bandwidth between you and each node. If you find that somebody is faster, you just talk to them more. If you find that something is slower, then you talk to them less. So you dynamically try to find out who to talk to. And ALTO server will remove that and make it faster. So a client can get the list of potential peers and send it to the server, which can return an ordered list. So a client can even say that, okay, all right, I got this list from whatever they call, I forgot the name of the nodes that give you the list of peers. Some of you might know it already. But anyway, so that list, you send it to the ALTO server, and ALTO server will say, well, I think these 4 nodes are near you, so talk to them. And then you need protocols for ALTO server discovery to talk to them and all that. So there is a whole set of protocols on that. So now it is being extended to locate resources in data centers. So when the data centers came in, then they said, okay, well, we do it already in the P2P. So why don't we do this in the data centers? When you want to know where is the router, where is this, where is the firewall, where is the load balancer, we can just go to the Alto server and ask them. So we need to be able to express what resource we need, what is the cost of these resources, what are the constraints on the resources I'm looking, what are the constraints on the structure, that I want something that doesn't consume too much power. And the Alto client can get the information from various providers. And so, for example, there might be many companies which might be offering the same information in the same data center. And they might say, well, I have a router which I can give you for $10, other may give you for $100, and so on, right? Issue of privacy of resource and cost of information for the provider. So the question is basically one of the issues in real implementation of Alto is that nobody may want to tell who has the file, or nobody may want to say, how much I charge and things like that, right? So that's an issue in the real world. But in data center, probably cost is not important because everything might be owned by one company, and then you just need to know where to go. So anyway, so there is a orchestrator on the top, as shown in the picture here. There is an Alto client which asks where to get the information, where to things, and then it can serve many data centers. It should be data center 1, data center 2, data center 3. Okay, and so that is Alto. A third protocol which became very popular is XMPP. XMPP was also done before SDN, and XMPP stands for Extensible Messaging and Presence Protocol. This is a protocol for chatting. Messaging means chatting. And we do chatting all the time. Even on the Facebook, when you do chatting, you are probably doing XMPP. Okay? So messaging protocol, and it is extensible, means it is not fixed. You can extend the protocol using XML. And so that is what the S is for. And it is similar to SMTP. SMTP is the mail protocol. So XMPP is similar to SMTP, but in SMTP what happens is when you send the mail goes to the server, and the server keeps it until the client comes up and says, okay, is there a mail for me? And it gives it to them. With XMPP, the client is generally always connected. And when the client is connected, you send a message, it is immediately delivered. And this is what happens to your texting or messaging or chatting. The both sides are continuously connected. And so the server doesn't have to store anything. It is not stored and forward, although it can be stored and forward, but generally you just are connected. So the client sets up a connection with the server. The client is online. And the presence, and presence is the same thing. Like when you are in the Skype, it tells you who is online. That is your presence. And messaging is when somebody is online, you send them a text. That is messaging. So the messages are pushed. So basically, the messages are pushed in real time. So basically, the client doesn't do anything. The server says, here is a message for you, and it gives it to them. Whereas in SMTP, you don't get anything until you ask for it. You can say, okay, can you give me a next message? And then we'll give you the next message. And you say, can you give me the next message? And you give you the next message. So on and so forth. So that is a pull protocol. Whereas XMPP is the push protocol. So there, as shown in the picture below, there are two servers. The server on the left, there are many clients there, and the servers on the right, there are many clients there. And these clients can share with each other because they're all connected continuously, right? So you guys all know about basically messaging at least, so you know how it works. So XMPP actually came from another protocol called Jabber. And Jabber was a proprietary protocol, so somebody took that Jabber protocol and converted that into standard, and so that was named XMPP. And there's an RFC on it. How do you do it? And you can use TCP or HTTP, and all messages are XML encoded. So that is another thing, is that basically they are XML encoded, just like HTTP. In HTTP everything is ASCII. Similarly here everything is ASCII, so it is not really efficient. If you want to send a binary file, You have to convert all of that into some ASCII characters using some codes. And so generally they don't use for file transfer. They just use it for text. And there are a number of open source implementations available for XMPP, and variations are used in the things that you use every day, like Google, in Google chatting, Skype chatting, Facebook chatting, and everything else. We use this protocol. It is used in IoT and data center for management. In the next slide, I will show you how you can use this chatting protocol for managing a data center. And so it is used in IoT and data centers for management. And the network devices have XMPP clients that respond to the XMPP messages. Actually, this all becomes very clear in the next slide. And actually, there's a company called Arista who started the switches that can be managed by XMPP. And Juniper is pushing this protocol very much. And so they wanted to have XMPP as the southbound protocol for SDN. And they bought a company called Contrail. And the Contrail is one of the standards which is being developed here where I came. So Linux Foundation is also developing another controller for another thing called Open Contrail, which has been renamed now. But Open Contrail is XMPP based. So these are the third protocol that can be used in place of OpenFlow. How can you use XMPP in data centers? So XMPP in data centers basically can be used as follows. On the left, I have shown the data center. On the right, I have shown something called XMPP server. And every device, including the user, including the controller, including every VM, every vSwitch, every hypervisor, and every pSwitch, everything has an XMPP client. So something that can understand the chat. Okay, which is very simple, right? It is XML based, so you can send an XML command saying, please come up, please change the route to this, please change that, change your entry in the table number 3. And so everybody can understand those messages, and there is a server. So any device can text to any other device. So a user can text to a VM can text to a pSwitch, a pSwitch can text to a vSwitch. So this is how a texting protocol can be used for communication between the machine-to-machine communication. And that is how XMPP is used. And believe it or not, this has become popular because it is very thin protocol. There is not much required in terms of implementation complexity. And so we now have Open Contrail. Okay. Any question about XMPP? Okay. All right. So now, Open Daylight picture, if you go back to, there are, what it can do is it can manage a whole network, and it can divide the network into segments. Each segment is for a tenant. So, for example, a network could be shared by 5 different companies, AT&T and T-Mobile in the same data center, and they could have their own virtual network segment. And so this is called Open Daylight Network Virtualization, ONV, and your network would be called Open Daylight Virtual Tenant Network, or VPN. So these are all the acronyms that fly by here: DNS, ONV, VPN, and so on and so forth. Generally, if you are doing this every day, you remember it, but if you're not doing every day, then you have to just refer to the acronym table to find out what VPN is. But anyway, services are Unified Secure Channel Manager is one example of a service. There actually are many other services. There are so many NAP-bound APIs, and so one of the NAP-bound API is REST. Now, I said REST, I will explain. Maybe I will try here, or maybe I will try a little bit more later. But REST stands for Representational State Transfer. Now, there is a PhD thesis of a student who came up with the idea, and he says that the best way to communicate is using representational state transfer. Basically, what it means is stateless communication, a communication in which I don't have to remember what I told you before. And so that is what we do in HTTP. HTTP is stateless in the sense that when you ask the server, please give me the next line of this table, you really don't ask for the next line. You already got line number 14 and you just say, okay, give me line number 15. So it doesn't have to remember what line number you got before. You just ask for whatever you need and it will give it to you and then forget it that it gave it to you. Actually, HTTP was supposed to work like that, but it turns out there are many things which need a state. For example, if you log in and you've already proven that you are who you are, then it will remember that, because if you have not logged into that device for 1 month, then it will remember that and say, oh, sorry, you haven't logged into the device for 1 month. Please prove you are, right? So nowadays, HTTP is no longer stateless. But originally as designed, HTTP was stateless, and for most applications where you don't put the security in front of it, it is still stateless. So that is called REST. So REST is best explained by an example, which is HTTP, and the keyword is stateless communication. So when two people communicate, so that they don't have to remember what the other guy had said before, and they can still give the answer, then that is called REST. REST is now configuration. Conf is configuration. So RESTful configuration. So basically, and again, these REST-conf and NetConf will be discussed in more detail in the last module of this course. But basically, when you do configuration of the devices, like DR Open Config, OS Config, or SNMP for management, you do that using some kind of RESTful API. Now, this is another word, RESTful. RESTful means basically REST. It simply means stateless. And so stateless configuration. NetConf is network configuration, which is the latest way of doing the configuration of devices and management of devices. And that is replacing what we used to call SNMP, Simple Network Management Protocol. Deluxe is that is the graphical user interface. And as I said, that it was developed, in this case, it was developed by Google for dynamic views, including AngularJS, which is some kind of Java. And so basically that dynamic views means things which are changing continuously. How do you do that? So Deluxe and GUI is used, and so it was developed by Google and everybody is using it now. AMQP is Advanced Message Queuing Protocol, and so this is message queuing we have seen in MQTT. It is similar to that. So AMQP is Advanced Message Queuing Protocol. And so if you need to know more about these, of course, you have to read a lot of stuff, but right now it is not critical for us. We are really interested in SDN, and so I think it is good enough just to know what they stand for. And then when you need, if you're really going to design a device, then of course you will need to find out what is AMQP and what is Deluxe and what is NetConf and RESTconf and REST and so on and so forth. Okay, so continuing on the southbound. So OpenFlow has a big plugin library and protocol library, and those include things like LIST. Now another protocol that you will hear a lot coming from Cisco and IETF in particular is called LIST. LIST is not the language. LIST is the locator ID separation protocol. So they came up with the idea that really we need to have, every device would have not only the locator, which is the IP address, but also the ID, so that I can know that this is your computer, Rajan's computer. And its IP address may be different at different times, but it is still the same computer. So we need to have like a MAC address and the IP address. MAC address is the ID, IP address is the locator. We need to separate these two so that the whole set of protocol are LIST. There is SNMP for SDN. SNMP for SDN is another version of SNMP for software-defined networking. BGP, Link State Path Control Element Protocol, PCE, Link BGP PCE protocol. Now BGP also has something similar to MPLS. In MPLS, you need a route like this. Well, in BGP, you may need a route which has lots of constraints. And so they have PC, the path control element protocol for BGP. Then on the bottom, we have the overlay, and we already talked about VXLAN. But then there is something called DOVE, which we didn't talk about, is Open Distributed Overlay Virtual Ethernet. And there are other overlays that can be implemented. Okay, which is like, so DOVE is actually similar to VXLAN, but does not use IP multicast. And then configuration. For configuration, we use YANG tools like NetConf or OVSDB. Now, what is YANG? YANG is another basically way of explaining what you need for configuration. And again, YANG is part of the last module in this course. So we will go through in detail as to how NetConf works, how YANG works, and why you need all that. So YANG and NetConf, you have to hold on to those thoughts, and we'll talk about them later on. OVSDB, we have already seen, Open vSwitch database, and that was how you manage an Open vSwitch using OVSDB. Okay.